Hello. So for this video, we will be talking about the definition and some characteristics of a differential equation. Okay. So by definition, or the very technical definition of a differential equation, so this is an equation wherein, okay, which involves, so rather, a differential equation is an equation which involves an unknown function. Okay, so any unknown function can be represented by symbols, say x, y, theta, alpha, etc. Okay, and its derivatives. So in a single equation, a DE will involve both the unknown function and its derivatives. Okay, so let's cite, or let's take note of some examples of some differential equations. Okay, DC. Example number 1, we have here dy over dx is equals to cosine of x minus sine of x. So in this example, we have x, an unknown function, and then its derivative dx. Y is another unknown function, and dy is its derivative. So this is an example of a differential equation. Another example, we have here x squared, right, plus y squared dx minus 2xy dy is equal to 0. Okay, so again, we have here the derivative of x, and we also contain, or the equation also contains x. We also have dy, which is the derivative of y, and the equation also contains y. Okay, so moving on to another example, we have here d squared y, or the second derivative, okay, plus 7 dy over dx raised to 3, okay, minus 8y is equals to 0. So this example shows that the differential equation does not only involve the first derivative, it can also involve the preceding derivative. So second derivative, third derivative, etc., etc. Also, the derivatives can be raised to a certain degree. In this case, the dy over dx in this example is raised to 3, right? So another example, we have here x, and then the partial derivative of f in terms of x, okay, plus y, and the partial derivative of y in terms of y is equals to n times f. So we have here f and its derivative in the same equation, y and its derivative in the same equation, x and its derivative on the same equation. So n, if not stated, is more likely a constant. Okay, this example also shows that a DE does not simply involve in an ordinary derivative. It can also involve a partial derivative. Okay, as long as the function is present, its derivative is present, it's a DE. Okay, and last example of a DE, we have here the partial derivative of y in terms of t is equals to h squared. Okay, and then second partial derivative of y in terms of x plus the second partial derivative of u in terms of y. Okay, so again, partial derivative is also valid for a differential equation. At the same time, its proceeding derivatives Okay, so I hope the definition or the technical definition of a differential equation is clear. So let's proceed to some characteristics of a DE. So first we have what we call the order of a differential equation. Okay, when we say order of a differential equation, this refers to the highest, okay, order of the derivative in the DE. So if the DE contains a first derivative, a second derivative, and then a third derivative, okay, then that DE will have a order of 3 or the third derivative. Okay, so in our previous examples, let's go back to our previous examples. Okay, let's try to determine the order of the previous examples that we have. Start with number 1. Okay, so for our example number 1 earlier, we have here dy over dx is equals to cosine x minus sine of x. So in this example, the highest derivative in this dE is dy over dx, or order of 1. So this dE will be on the first order. Okay. Next, we have here x squared plus y squared dx minus 2xy dy is equals to 0. So we have dx, which is a first order derivative. We have dy, which is also a first order derivative. No other derivatives. So we can say that the highest order here is 1. Okay, so number 2, or the second example, will be another first order derivative, right? For our third example here, we have the second derivative of y in terms of x plus 7 times the derivative of y in terms of x raised to 3 minus 8y is equals to 0. Now we have two derivatives here, dy over dx, which is of the first order, and then uh, the second derivative of y in terms of x, which is in the second order. So the highest derivative or the highest order derivative here is the second order. So this dE will be of the second order. Now, moving on, we have our example number 4. So we have the partial derivative of x in terms of x, first order, partial derivative of f if in terms of y, also in the first order. Okay. Next, 5. So partial derivative of y in terms of the first order, partial derivative of y in terms of x second order, partial derivative of u in terms of y also second order. So the highest order derivative here is 2. So for the example number 5, this will be of the second order. Okay, so I hope the order of a differential equation is clear. So let's move on to the next example, or rather next characteristic of a DE, which is the degree of a differential equation. So for this characteristic, we are defining the degree of a DE as the exponent, okay, of the highest order derivative. Okay, or the rather the highest exponent of the highest order derivative. Okay, so let's go back to our examples earlier and let's try to determine the degrees of the examples. Okay. Okay, so for our first example earlier, we have dy over dx is equals to cosine of x minus sine of x, as we have determined that this is of the first order. Okay, so this is the highest order derivative and its exponent is 1. So we can say that this dE is of the first degree. Okay, because the highest order derivative again is raised to 1. Second example, dx and dy is our highest order derivatives and they are all raised to 1. So we can also say that the second example is of the first degree. Okay. Next, number 3. So we have the second derivative of y in terms of x, and then we have the derivative of y in terms of x raised to 3. Although the highest exponent here is 3, but this is the exponent of not the highest order derivative. Our highest order derivative is the second derivative of y in terms of x, and it is only raised to 1. So the degree here will still be of the first degree. Alright, then for the example number 4, okay, so again, first derivative, all raised to 1, first degree. Okay, example number 5, second derivative, all raised to 1. So still of the first degree. So all of our examples are of the first degree. Alright, so hopefully the characteristic of the DE, which is the degree, is clear. So let's proceed to the next characteristic. Okay, so for a solution, rather for an equation to be considered a solution of a DE, after the verification process, it should equate to 0. Okay, if not 0, then at least it will balance the equation. So for example, if we have here a DE second derivative of y in terms of x plus the first derivative of y in terms of x minus 6y is equal to 0, and we want to verify if, okay, we want to verify if y is equals to e raised to 2x is a solution to this DE. Okay, so what we will do is we will substitute this to our differential equation, but in our differential equation we have the first derivative and then the second derivative as well. So let's try to get the first derivative and the second derivative of y is equals to e raised to 2x so that we can substitute it to our differential equation. So for the first derivative, that will be equal to 2 e raised to 2x. Okay, then for the second derivative, so we will differentiate the first derivative. So this will be equal to 2 times 2 e raised to 2x, okay, or equal to 4 e raised to 2x. Alright, so this will be our, okay, so this will be the terms that we will introduce to our differential equation. So for our differential equation, which is the second derivative of y in terms of x, okay, which is also y double prime, plus the first derivative of x, of y in terms of x, which is also the first, or rather y prime. Okay, then we will substitute y double prime is 4 e raised to 2x, right? Plus the first derivative, which is 2 e raised to 2x minus 6 times y, and our y is e raised to 2x equal to 0. Now simplifying, we have here 4 e raised to 2x plus 2 e raised to 2x, which will be positive 6, okay, minus 6 e raised to 2x. So 6 e raised to 2x minus 6 e raised to 2x, and they will cancel out. So we have 0 is equal to 0. And since the equation is now balanced, we can say that y is equals to e raised to 2x is a solution. Okay? Now let's have another example. Okay, so for the next example of our solution of a DE verification, so we have here verify if x is equals to sine 80, okay, is a solution to the second derivative of x in terms of t plus k squared x is equal to 0. Alright, so this will be our example. Now to confirm, we need x, we have x here, and we need the second derivative as well in order for us to substitute this to our differential equation. So we have x is equals to sine of kt, right? So if you're confused, let us place a parenthesis here. So we need the second derivative. Of course, we cannot skip directly to the second derivative. So let's pass through the first derivative first. So the derivative of sine of kt, we need to do a little bit of chain rule here. So the derivative of the sine of kt will be cosine of kt. Okay, so this one will be in terms of t. And then, if you're being confused by the prime, let's write it this way. Okay, so dx over dt, right? So we are deriving sine of kt in terms of t. So the derivative of sine is cosine kt, and then the derivative of the inside of the parenthesis will be k. Okay, or this will be k cosine of kt. Next, for the second derivative, right? So this will be the derivative of, again, k cosine of kt. So the derivative of cosine first, that will be k, then negative sine of kt, right? And then let me rewrite this a little bit first. Okay, so instead of using parenthesis here, let's use a bracket. Okay, that will do. Then the derivative of the inside is also k, or inside the parenthesis. Now let's simplify. So we have k here, we have k, we have negative. So negative k squared sine of kt. Now let's substitute this to our differential equation. So d squared x dt squared plus k squared x is equals to 0. Substitute the second derivative, which will be k squared sine of kt, right? Plus k squared. Then substitute x, which is sine of kt, right? Then we have equal to 0. So negative k squared sine of kt, positive k squared sine of kt. So this will cancel out. So we will have 0 is equals to 0. The equation of is balanced. So therefore, okay, therefore, x is equals to sine of kt is a solution. Okay? To the second derivative of x, right, plus k squared x is equal to 0. So this will be the answer. Alright, so hopefully the concept of the solution of a differential equation is clear. So let's proceed to the next characteristic. Okay, so for the next characteristic, we have the partial versus ordinary DE, or differential equation. Okay, so simply put, if the DE involves a partial derivative or partial differentiation, then that is considered a partial DE. If there is no partial derivative, then that is an ordinary DE. So if we go back to our examples earlier, okay, so first example, again, we have dy over dx is equals to cosine of x minus sine of x, ordinary DE, because it does not involve any partial differentiation. Number two, also ordinary DE, Number 3, also ordinary DE. Number 4, since this involves partial derivatives, then this is a partial DE. And also number 5, this is also a partial DE. Okay, so I hope the concept of partial and ordinary DEs is clear. So let's proceed to our next characteristic, which is linear versus nonlinear DE. Okay, so I will list here some important characteristic for a linear DE, or rather, what should we look out for in a DE so that we can say that it is linear. Okay, so first, the dependent variable. Okay, so the dependent variable and its derivatives should be raised to the power of 1 only. So the dependent variable and its derivatives. Okay, and its derivatives should be raised to the power of 1 only. Or are raised. Okay, are raised to the power of 1. To the power of 1 only. Okay, number 2. There should be uh, the dependent and the dependent variable and its derivatives. Okay, so how should I write this? Okay, so the variable and its derivatives are not in any nonlinear functions. Nonlinear functions includes trigonometric functions, logarithmic functions, etc., etc. Okay, and then number 3. So again, the dependent variable and its derivatives are not multiplied to each other. Okay, so let's recap. So for a DE to be considered linear, first, the dependent variable and its derivatives are raised to the power of 1 only. Okay, second, the dependent variable and its derivatives are not in any nonlinear functions. The dependent variable and its derivatives are not multiplied to each other. So if any of this rule is not followed, then the DE is nonlinear. Okay? Now, these rules follows or are applicable both to partial and ordinary DE. So let's have some examples of a linear and nonlinear DEs. We can classify and see. Okay, so for the first example, we have here dy over dx plus open parenthesis 1 minus x close parenthesis times y is equals to ln of x. Okay, so let's check if this DE is linear or nonlinear. So again, the first rule of a linear DE should be the derivatives and its rather the dependent variable and its derivatives should be raised to the power of 1 only. So in this case, our dependent variable is y. Okay, so y here is raised to 1, dy over dx here is raised to 1. So the first rule is followed. Okay, First rule is followed. Second rule, the dependent variable and its derivatives should not be inside any nonlinear functions. So we have a nonlinear function here, which is ln, or natural logarithm, and it contains x, which is the independent variable. So the dependent variables are safe from this nonlinear function. So the second rule is followed, or rather complied. Then number 3, all right, so the third rule is the dependent variable and its derivative should not be multiplied to each other. So we have the first derivative here, we have the y here, and what is multiplied to y is 1 minus x, which is not its derivative. So the third rule is also followed. So the three rules are complied to. So this one is a linear function. Okay, so let's have another example. Okay, so for our second example, we have here y double prime minus 6y prime plus y is equals to x minus e raised to y. So let us determine if this example is a linear or a nonlinear DE. Okay, so first rule again, the dependent variable and its derivative should be raised to 1 only. So we have the dependent variable here as y, because the other derivatives are y prime and y double prime. Okay, so raised to 1, raised to 1, raised to 1, raised to 1, raised to 1. Complied. First rule, complied. Second rule, the dependent variable and its derivatives should not be included in any nonlinear functions. Okay, and since we have here y as the exponent of e, so y here is inside the exponential function, which is nonlinear. So this violates, or rather this does not comply to the second rule. So therefore, this DE is non-linear. Okay. Now for the third rule, uh, since we have already determined that this is nonlinear, but we will still check for the third rule. The third rule states that the dependent variable and its derivatives should not be multiplied to each other. So in the first term, you have y, the dependent variable, multiplied to its second derivative. Okay, so this is also a this also indicates that this is non-linear. Okay, and then let's have another example. Okay, for the third example, we have here, this one, by the way, is an indication of third derivative. So p raised, rather, apologies, third derivative of p. This is an notation, a notation of derivative as well. So third derivative of p minus x cubed, uh, p double prime, or the second derivative of p, plus e raised to xp is equals to p squared. Okay, so if we will go back to the, if we will verify if this is a linear DE or not. Okay, so the first rule again is for the call this one, the dependent variable and its derivatives should be raised to 1 only, right? So this a third derivative of p is raised to 1. Second derivative of p raised to 1. P is also raised to 1. The problem is we have here p squared, which is the dependent variable raised to 2. So because of this, we can say that this is a nonlinear DE. Okay. So this is a nonlinear DE. But if we will try to uh, compare this third example to the other rules. Second rule, the DE should not be inside any nonlinear functions. So, or rather, the dependent variable and its derivatives should not be inside any nonlinear function. The only nonlinear function here is e raised to x, and e raised to x is multiplied to p, so the p is not inside the exponential function. So number 2 is clear, and then the number 3 rule is the function should, but rather the dependent variable and its derivative should not be multiplied to each other. So this is the third derivative, not multiplied to the second derivative, not multiplied to p, not multiplied to p squared. Okay, so second and third rule should have been cleared, but the first rule is not. So this DE is still nonlinear, right? So hopefully the characteristic of a linear and nonlinear DE is clear. So to recall what we have discussed so far in this video, so we have discussed the technical definition of DE, we have discussed the uh, order, degree, dissolution, the partial and ordinary DE, as well as the linear and nonlinear DE, which are the characteristics of a differential equation. So that's it for this video. See you on the next video.